In this example, we need to find the distance between a point and a plane using this equation. So here we have our point and we have our plane. But first we need to see if the point lies on a plane, because if it does, then the minimum distance is 0. So first we need to plug in this point into the plane. So we have 2 times 3 plus 3 times negative 4 minus 4 times 6. So here we get negative 30 equals 8. So left side does not equal right side. That means point P is not on a plane. Since left side does not equal right side, we know that point P does not lie on a plane. So next we need to have our normal vector, which is 2, 3, negative 4, which we found just by the coefficient of the plane. And now we need to find vector PQ. To find the vector Q, we can choose any point on the plane by selecting arbitrary values for x, y, and z. So we can say x equals 4, y equals 0, and z equals 0. So point Q equals 4, 0, 0. Now that we have vector Q, we can use that to find the projection of vector PQ onto the normal vector, which gives us the distance that we require. So assuming that vector O is 0, 0, 0, vector OQ is going to be 4, 0, 0, subtract vector OP, which is 3, negative 4, 6, which is going to give us 1, 4, negative 6. That is vector PQ. Now that we have vector PQ and our normal vector, we can use those values and sub it into our distance formula. So since I've done it here, this is going to give us 38 over square root of 29, which is going to be our distance from the point to our plane. In this next example, we have a plane flying on the plane 5x plus 2y plus 6z equals negative 1, and the lamppost at point P, negative 1, 7, and 2. So for part A, determine if the plane will make contact with the lamppost. So we can assume that point P is the top part of the lamppost. So basically what part A is asking is, does point P land on the plane? So to find out, we can sub in the point into the plane and see if both sides equal each other. So now I plugged it in. This side equals 21 and the right side equals negative 1. So left side does not equal right side, which means that point P does not land on the plane, and so the plane does not make contact with the lamppost. For part B, we need to find the distance between the plane and the lamppost. So we need to find our normal vector, which is going to be 5, 2, and 6. Remembering that is the coefficients in front of the variables. And we need to find our point Q. Remembering from the equation, vector n, which is our normal vector, times PQ over the magnitude of the normal vector. For point Q, we can choose any point on the plane by selecting arbitrary values for x, y, and z. So I'm going to choose 5 for x, 0 for y, and 0 for z. Now that we have vector Q, we can find the projection of vector PQ onto the normal vector, which gives us the distance that we want. So to find the projection of vector PQ, we can do vector OQ subtract vector OP, assuming that vector O is 0, 0, 0. So it's going to be 5, 0, 0 subtract 1, negative 1, 7, 2, which is going to give us this is our value for PQ, which is also the projection. Now that we have our normal vector and our PQ vector, we can sub in those values into our distance formula. So it's going to be the absolute value of our normal vector, which is going to be dot product with our vector PQ, over the magnitude of our normal vector. This is going to give us the distance of 28 over square root of 65. Therefore, the distance between the point and the lamppost is 28 over square root of 65, which, if we simplify it even further, is going to give us 3.47 units.
So we know that lines can intersect with planes in 3 different ways. Firstly, they can intersect at a specific point with a plane, meaning that there is one unique solution. Secondly, the line could lie on the plane, meaning that there is an infinite number of solutions, as there would be multiple intersection points. Lastly, the line could be parallel to the plane, meaning that there are no solutions, as there is no point of intersection occurring.